A spectrophotometer is an analytical instrument used to measure the intensity of a light beam at a fixed wavelength as it passes through a solution. In simple terms, the result can be displayed in two ways. Firstly, as transmission, the amount of incident light that passes through the solution, or more commonly as absorbance, the amount of light that is absorbed by the solution. It should be obvious that more light will be absorbed by a more concentrated solution. Therefore, this is a simple and yet powerful technique to determine the concentration of a solution from its absorbance. This video is designed to show you how to set up and use the spectrophotometer. More information on the background theory to the method is given in your lab schedule. Start by removing the cover and turning on the machine using the switch on the right hand side. It will take a few minutes for the machine to calibrate itself. While this is happening, you should prepare your samples. Here we have two different samples of copper sulfate. This one is prepared to a concentration of 50 millimolar and this one to a concentration of 25 millimolar. You can see that the less concentrated solution appears paler. We will use a spectrophotometer to measure their respective absorbance. To measure the absorbance, around 3 millilitres of the solution is transferred to either a plastic, glass or quartz cuvette. The cuvette is 1 centimetre wide by 1 centimetre deep, thus giving the light a distance of 1 centimetre to travel through the solution. Check your lab schedule for more information on path length. Notice that two sides of the cuvette are not transparent. This is important when positioning the cuvette in the spectrophotometer. If the frosted side was in the line of the light beam, this would affect the result. You can now set up the spectrophotometer. You can see that the display is set to show percentage transmission. It is more common to measure light absorbance, and you will not work with transmission during this course. To change the display from transmission to absorbance, you press number 2 as shown on the instrument display. This then changes the measurement to absorbance. You now need to select the correct wavelength of light. You should recall that things appear different colours as they absorb different wavelengths of light in the visible spectrum. When working with solutions, you can start by testing a range of different wavelengths in order to determine the most suitable wavelength for that particular solution. Here we are working with copper sulfate, which has an optimum wavelength of 810 nanometers. So to set the wavelength, press Go to WL and enter the value 810 and press Enter. It may take a few seconds for the machine to recalibrate. Open the flap on the front of the spectrophotometer and you will see a metal carriage with spaces for 4 cuvettes. The position of the carriage can be adjusted using the lever on the front of the machine. Before taking a measurement of a sample solution, you should always take a blank measurement using a solution of 0 concentration. The copper sulfate solutions were prepared in deionised water, so this cuvette containing only deionised water is the most suitable blank to use. The cuvette containing the deionised water should be placed into the first slot in the carriage, and you should ensure that the clear side faces the slit in the side where the light beam will emerge. The 2 copper sulfate solutions are then placed in positions 2 and 3, and you should ensure that the front lever is pushed back so that the blank solution is in the path of the light beam, and close the lid. The display will now show you the absorbance of the pure water and any interfering absorbance from the cuvette itself. In practice, this is a very low value. To produce accurate results, the machine must deduct this figure from the sample measurements. This means that only the absorbance of the copper sulphate is displayed. To do this, you should press Auto 0. Do not worry if the number starts to fluctuate a little, this will not have any significant effect on your result. Now slide the front lever to the first click. This will move the internal carriage so that the first cuvette containing the 50 millimolar solution is in place. You can see that the absorbance of this solution is displayed as 0.883. Now slide the front lever to the next click. This will move the internal carriage so that the cuvette containing the 25 millimolar solution is in place. You can see that the absorbance of this solution is displayed as 0.451. By comparing the two values, you can see that the more concentrated solution has a higher absorbance compared to the lower concentration. Also notice that as the concentration doubles, the absorbance is also approximately doubled. This linear increase in absorbance proportional to concentration is the basis of the Biot-Lambert law. This law is obeyed up until an absorbance of 1.0 to 1.5, after which the absorbance increase would start to tail off. Therefore, if you were to have a range of absorbance values for different known concentrations, you could plot a graph of absorbance against concentration and use this to determine the concentration of an unknown solution by measuring its absorbance. For more information on calibration graphs, see the lab schedule and other videos in this series. Once your experiment is complete, you should carefully open the lid and remove all cuvettes. You should take care not to spill any solutions in the machine. You should then push the lever back fully and close the lid. Finally, you should switch the machine off and replace the dust cover. You should rinse out the used cuvettes with deionised water for reuse or dispose of them into the waste bin. To test your understanding, please complete the short quiz on the KLE.